When thinking of colossal hydroelectric megaprojects, we instantly picture the mighty Three Gorges Dam spanning the Yangtze River in China, or the massive concrete wall of the Hoover Dam towering over the arid canyons of the American West. Yet, few know that in Ethiopia, a nation located in the far east of the Black Continent, known as the Horn of Africa, is currently harboring an even more controversial and staggering megaproject. Before your eyes stands the largest hydroelectric project in Africa, the Grand Ethiopian Renaissance Dam, or GERD for short. A massive concrete wall standing up to 145 meters tall and nearly 1.8 kilometers long, swallowing tens of billions of cubic meters of water from the legendary Nile River. It is not only a source of national pride that completely reshapes the energy map of an entire country, but it has also triggered one of the most intense water disputes on the planet, putting downstream Egypt on high red alert. How did Ethiopia conquer a ferocious flow to build this massive concrete wall? What terrifying technical challenges lie hidden beneath? And why has this project dragged the nations along the Nile banks into an endless geopolitical conflict? We will explore all the details in today's video. Before we begin, don't forget to leave a like to support the channel, my friends. And now, let's get started. To understand why this mega project was implemented, we need to analyze the allocation system of the Nile River flow. Decades ago, colonial-era treaties granted exclusive control over the vast majority of the Nile's waters to downstream nations like Egypt and Sudan, or rather, stripping upstream basins of their exploitation rights. Meanwhile, Ethiopia, the nation supplying up to 85% of the total water volume of the Nile system, suffered from severe energy shortages and crippled infrastructure. More than half of its population lived in darkness. This urgent need for energy pushed tensions to a boiling point. For Egypt, the Nile is the lifeline providing 90% of fresh water for its arid downstream region. The core dispute centers on the filling timeline of the reservoir, which has a capacity of 74 billion cubic meters. Ethiopia wanted to shorten the filling period to 3 to 5 years to quickly operate all power-generating units, while Egypt and Sudan demanded an extended roadmap of 12 to 15 years to prevent widespread drought risks. International negotiation rounds repeatedly collapsed due to conflicts over river flow control. Despite stern warnings and the visible threat of armed conflict, Ethiopia decided to turn political pressure into practical action. In April 2011, the official groundbreaking ceremony of the GERD megaproject took place in the Guba Valley, turning a diplomatic standoff into a massive construction site. To construct on the flow of the Nile in the Guba Valley, engineers had to solve a massive mechanical and hydraulic problem. The first and mandatory step for any hydroelectric dam is to divert the natural river flow. The construction team excavated a large diversion channel with a large cross-section through the right mountain slope, capable of swallowing a flow rate of thousands of cubic meters of water per second. Next, 2 load-bearing cofferdams, including an upstream cofferdam and a downstream cofferdam, were erected to completely block the main flow and completely isolate the river section in between. The upstream cofferdam, standing about 50 meters high and hundreds of meters long, withstood direct water pressure from upstream, combined with the downstream cofferdam blocking backflow from below, ensuring the foundation pit in the middle remained completely dry. After isolating the area, dozens of high-capacity pumps operated continuously to completely drain the water inside the foundation pit, exposing the ancient granite bedrock at the riverbed. This foundation surface was immediately treated using high-pressure cement grouting, with thousands of drill holes ranging from 20 to 50 meters deep. This grout seeped into and sealed every underground geological fault, creating a monolithic structural base capable of supporting a static load of tens of millions of tons for the entire dam body. Once the foundation pit was dry and met safety standards, the massive construction site entered the concrete pouring phase. The main dam body is a giant gravity structure with a length of 1,780 meters and a height of 145 meters. To optimize speed, engineers used roller-compacted concrete (RCC) technology. More than 10.3 million cubic meters of dense concrete were transported continuously by an automatic conveyor system stretching for kilometers, then compacted by high-power vibratory rollers to achieve maximum material density. However, this massive volume of material generated a critical physical hazard: the heat of hydration. When millions of cubic meters of concrete hardened at the same time, the temperature inside the dam core would soar to over 50 degrees Celsius, causing expansion and cracking throughout the structure. To eliminate this heat, a mandatory technical solution was applied: building a large-scale refrigeration plant system right at the construction site, producing over 1,500 tons of ice daily to completely replace mixing water in the concrete batch, keeping the mixture's temperature below 12 degrees Celsius before construction. At the same time, in nearby valleys, a concrete-faced rock-fill dam, CFRD, with an exact length of 5.2 kilometers and an average height of 50 meters, was also built. This structure sealed the topographical perimeter, allowing the entire system to hold a massive water volume of up to 74 billion cubic meters. Finally, 6 radial gates with a total discharge capacity of up to 14,700 cubic meters per second, along with steel penstock pipes 8 meters in diameter, were directly integrated into the dam body. These pipes channeled high-velocity water directly to operate France's turbine units. With a total design capacity of 5,150 megawatts, the mechanical energy of the water flow officially turned GERD into the largest power plant in Africa. After overcoming the mechanical challenges and harsh foundation treatments in the Guba Valley, the GERD megaproject officially entered the next challenging phase: reservoir operation and water filling. The reservoir filling process was implemented in stages starting in July 2020. Each rising water level was closely monitored through a geotechnical survey sensor system. Parallel to the filling process, the first France's turbine units were successively put into operation starting in 2022. By September 2025, the project officially completed all core components and was comprehensively inaugurated, bringing the total installed capacity of the entire plant to 5,150 megawatts, making GERD the largest power plant on the Dark Continent. The completion of this mega project created a true revolution in the lives of the Ethiopian people. Before the dam appeared, more than half of the country's population lived in severe power shortages, with hospitals, schools, and production facilities constantly disrupted due to an overloaded national grid. When the massive flow of electricity from the GERD hydroelectric plant integrated into the national grid, tens of millions of people gained access to stable electricity for daily life for the first time. Industrial zones emerged, agricultural irrigation systems were electrified, and millions of households escaped the need to use firewood for daily life. The dam officially erased chronic energy shortages, pushing Ethiopia into an era of industrial self-reliance and strong economic development. However, while the upstream brightened with electricity from GERD, downstream Egypt sank into unprecedented survival pressure. The trapping of tens of billions of cubic meters of water in Ethiopia directly choked the natural flow heading to the delta, threatening to turn the breadbasket of the southern Mediterranean into arid lands. Faced with this life-or-death problem, Cairo did not sit still waiting for disaster. They were forced to activate national-scale technical strategies to save themselves by reshaping the hydrological flow. Egypt poured full effort into deploying massive artificial canal megaprojects, recycling agricultural wastewater through billion-dollar water treatment plants, and turning barren desert regions into new artificial water routes to make up for the shortage from the Upper Nile. How large is this counter-strategy, and how does the structure of that second artificial river operate? If you want to discover in detail how Egypt fights back against the water crisis, look back at the video, Egypt is building a new Nile River, right on our channel. The Grand Ethiopian Renaissance Dam stands there as an emblem of the industrial age. The massive concrete wall has reshaped the future of an entire river, while leaving an unresolved puzzle regarding resource security in this century. In your opinion, is it fair for an upstream nation to have full control over a life-or-death river flow, or must the downstream accept this new order? Leave your thoughts in the comments below. Don't forget to subscribe to the channel and hit the notification bell so you won't miss in-depth analyses of upcoming engineering megaprojects.